All right, let's see how to do an application problem using definite integrals. It's really important that it says the marginal cost of printing a poster when X posters have been printed is given by this equation. It's really important that this is the marginal equation, because if it's the marginal equation with the derivative, then that means that we can find total costs by finding the antiderivative. Find the cost of printing 64 more posters when 16 have already been printed. That means we're finding the integral of 16 to 64. Now you might be wondering, how come it might get more cheap or more expensive to produce more or less of something? And the reason is because of something called economies of scale, which you can learn about in economics class. But in general, the more you produce of something, the cheaper per unit it is to make it. Probably not for just making a couple posters, but certainly for making thousands and thousands of something. In any case, we just need to figure out this integral. The integral from 16 to 64 of x to the negative 3/4 dx. This will equal, we need to figure out what would be the derivative of this, and the answer would be x to the 1/4 divided by 1/4, evaluated from 16 to 64. So before I move on, let's take a real hard look at that and make sure that's accurate. If we took the derivative of this, the 1/4 would come down, which would cancel the 1/4. We would subtract 1 from 1/4, which would get us negative 3/4. So that is my correct antiderivative. I'm going to rewrite this as follows. 4x to the 1/4, because dividing by a fourth is the same thing as multiplying by 4, evaluated from 16 to 64. So that's 4 times, I'm going to rewrite x to the 4th as the 4th root of 64, minus 4 times the 4th root of 16. Okay, so that's what x to the 4th means. And if we think about it, 4 times 4 times 4 times 4, oh, it's not going to be 64. Darn, I was hoping it was. 2 times 2 times 2 times 2 is definitely 16, though. So that's going to be 8, because the 4th root of 16 is 2, because 2 times 2 times 2 times 2 is 16. So 2 times 4 is 8. And then the 4th root of 64, let's see, I think we can pull off the 16, so that'll be 2 times the 4th root of 4. So we get 8, because the 2 multiplies. So that's about as nice as you can make the answer right there, or you can turn it into a decimal. So all I did right here was I pulled off the 16 and the 4, and the 16 comes out, becomes a 2, multiplies, becomes an 8. So 8 times the 4th root of 4 minus 8, or you could just turn it into a decimal. All right, let's take a look at this application problem. This is something very interesting. In physics, you have a position equation. If you take the derivative of the position equation, you get velocity. And if you take the derivative of velocity, you get acceleration. And so that's what's really cool. If you have your position equation, take the derivative of it, you get the rate of change of that, which is velocity. Take the derivative of the rate of change of velocity, and you'll get acceleration. That's by doing derivatives, f prime, f prime. You can also go backwards by doing integrals and by doing antiderivatives. So if you take the derivative of the antiderivative of f and the antiderivative of f, you can also work backwards. So here you can see that we're given an, I'm sorry, it's a little blurry. Here you can see that we're given an acceleration equation, a of t equals negative 18t plus 6. Let's do the antiderivative of that to get the velocity equation. So the antiderivative of negative 18t plus 6, that's going to equal negative 18t squared over 2 plus 6t plus c. Don't forget, we need that plus c if we're not doing a definite integral like we were in the previous section, in the previous video. All right, so that's going to mean that our velocity equation, v of t, is equal to negative 9t squared plus 6t plus c. Notice that they give us an initial condition of v of 0 equals 5, so that helps us knock out this plus c like we saw in a previous video. So 5, the value is equal to this when we plug in a 0. So boom, boom. So that means our first c is equal to 5. So our new equation is negative 9t squared plus 6t plus 5 is equal to velocity. We can find, oops, I'm sorry, I left off my dt. There should have been a dt right there. Now we can find the position equation by doing the next integral and taking one more integral dt. So that's going to be 9t cubed over 3 plus 6t squared over 2 plus 5t plus c. I know I did that pretty quickly, but double check my work to make sure those are all of the correct answers, and I believe they are the correct derivatives. So that's going to be negative 3t cubed plus 3t squared plus 5t plus c is equal to our position equation, s of t. Now they give us another initial condition, so we can do another initial condition to figure out what this c is. And when we plug in 0 everywhere, we get 6. So that means that our actual final equation for position is negative 3t cubed plus 3t squared plus 5t plus 6. There you go. Derivative of this is your velocity equation. Derivative of velocity is your acceleration equation. Now, you notice, again, I stress that c is not always going to be equal to what your initial condition is. It just is quite frequently, because when you plug in a 0, it tends to knock out lots of terms, and so you just end up with the constant. One nice thing about 0 is it makes sense for 0 to be an initial condition, because we start at 0, and so one nice thing about that is that it can clean up our equations very nicely. That concludes section 4.3. We're going to start section 4.4. I hope you're enjoying integrals and definite integrals, and I will see you in the next section.